Hello students, I am Dr. S.M. Bhatti. The objective of this video is to study first shifting property, second shifting property and division by t property of Laplace transform. We have seen first four properties of Laplace transform in previous videos. Let's study now fifth property, division by t property. If Laplace transform of function small f of t is a capital F of s, then Laplace transform of ft upon t is equal to integration from s to infinity capital F of s ds, provided that ft upon t exists as t tends to 0. That means if we know Laplace transform of function small f of t as a capital F of s, then we can find the Laplace transform of that function ft upon t by integrating this capital F of s with respect to s from the limit s to infinity. Let's see an example here. Find or determine the Laplace transform of sine square t upon t, and in addition to this we have to evaluate the integral from 0 to infinity e raised to minus t sine square t upon t dt. The Laplace transform of sine square t can be evaluated by the following calculations. So first job, because we want to find Laplace of sine square t upon t, and which has a type Laplace of f of t upon t. So f of t became sine square t. So your job is to find the Laplace transform of sine square t first. So Laplace of sine square t is equal to, now Laplace of sine square t is not directly possible. We have to convert this sine square t in some simple function, and we know formula sine square t is equal to 1 minus cos 2t upon 2. Then you can split this ratio in two terms, 1 upon 2 minus 1 upon 2 cos 2t. So you will find here two terms in the bracket. Laplace of these two terms will be very easy. Apply linear property, apply the table, first table to find the Laplace transform. In first term 1 upon 2 will come out, and Laplace of 1 became 1. Laplace of 1 became 1 upon s. That is, Laplace of first term is 1 upon 2 into 1 upon s. That is 1 upon 2s. In second term second term will have the minus sign. Okay, 1 upon 2 is constant, it would come out, and that is multiplied by Laplace of cos of 2t, and Laplace of cos 2t is s upon s square plus 4. Now just you make a cross multiplication here, and you can find it is a 2 upon s square 2 upon s into s square plus 4. In fact, we don't need to simplify this, because this function is easy to find the what is called as a inverse Laplace transform. Anyway, what we are going to do here, we are applying the property. So this property we are applying now. This property we are applying. Laplace of ft is capital F of s. So we obtain Laplace of sine square t as a capital F of s. Hence now we can obtain Laplace of sine square t upon t by taking this capital F of s here in the integral, and then evaluate this integral. You can get the required Laplace transform. So here for this step, you can see that this is a small f of t, and this is the capital F of s. This is, you can treat this expression as a capital F of s and apply the property. So according to property, Laplace of ft upon t is equal to integration from s to infinity of capital F of s ds. This is easy for the calculation. So this is capital F of s we have taken here, because integration is easy for this expression. It is 1 upon 2, and you can see that integral of 1 upon s is a ln s minus 1 upon 2, and you can see here you require to multiply by 2 and divide by 2 so that the derivative of denominator became numerator, so that you find here minus 1 upon 4 ln of s square plus 4. So here grid adjustment is here, and then you apply the properties here. I think you can do one thing here. You can multiply here, multiply, divide by 2, multiply by 2, divide by 2, multiply by 2. That multiply by 2 can be taken to the power of s, and then you can take the 1 upon 4 common between these two terms. You will get 1 upon 4 common. Of course, you have to multiply by 2 and divide by 2 in the first term, and the divided by 2 keep as it is, so that you find your 1 upon 4, and the multiply by 2 can be taken to the power of s, so that you will find your 1 upon 4 ln of s square. Now apply the property. 1 upon 4 will be common, and you take the 1 upon 4 out, and you know the formula. ln of p minus ln of q is ln of p upon q. So you find this, and here limit of s are s to infinity. First we put s is infinity, but when you put infinity here, what is happening here? If you put s is infinity here, as you can understand, that infinity upon infinity form. So better you take the s square common from the denominator. So if you take s square common from the denominator, you'll find in denominator 1 plus 4 upon s square, and s square will get cancelled, and you'll find as a s tends to infinity, you'll find ln of 1, and ln of 1 is 0. The seconds, and then there will be minus sign. You have to put s there, so remain as it is, and you can absorb that minus sign by taking the power of this quantity. So that I mean to say that when you simplify this, you will find it is a 1 upon 4 ln of s square plus 4 upon s square. I told you here, taking s square common here and taking the limit as s tends to infinity, you will find it is a 1 upon 0, 1 upon 1 plus 0. That means ln of 1 and ln of 1 is 0. Okay, so let's complete now second part. In second part, we have to evaluate this integral. We have to evaluate this integral, and you can see that we can, if let's make a change here. Instead of writing e raised to minus t, if I write e raised to minus st, the same integral became this. Are you understanding? Now we want to evaluate this integral. How to read this integral? How to understand this integral? Integral from 0 to infinity e raised to minus t sine square t upon t dt. So this sine square t upon t is taken as f of t, and this is, there is exponential expression e raised to minus t. So this I will treat this as a f of t, and this is a e raised to minus st type. So I mean to say that here is e raised to minus t, e raised to minus t. I will treat this as e raised to minus st. So this actually, because we want to introduce s here, so that I can use a definition of Laplace transform. So this can be treated like this. This I will treat like this. No doubt, if I put s as a 1, I can get this. But this is nothing but the Laplace of sine square t upon t. This integral is nothing but the Laplace of sine square t upon t. So we can find it separately. And already in last example we have obtained it. It is 1 upon 4 ln of s square plus 4 upon s square. And required integral is obtained by taking s as a 1. So in this expression we have to put s as a 1. That's it. So required integral, to get the required integral, we have to put s equal to 1 on the both side of this equation. So when you put s equal to 1, you will find this. And here actually there is s is not available directly, but value of this quantity is already we obtained in the few minutes back. We obtained Laplace of sine square t upon t. So write that, and there you put the s is a 1. So when you put s is a 1, you will find the answer of this integral as a 1 upon 4 ln of 5. Let's see now sixth property, shifting property. It is a first shifting property, or it is also called as first translation property. It is also called as S shifting. So if Laplace transform of the function small f of t is a capital F of s, then Laplace transform of the product e raised to at into f of t is capital F of s minus a. That means if Laplace of small f of t is known as a capital F of s, then we can get Laplace of the product of this function f of t with e raised to at by replacing s by s minus a in the right side. And if you change the position of the operator L, you can have the property for inverse transform, inverse Laplace transform. This is a property for Laplace transform, and this is a property for inverse Laplace transform. According to this, if L inverse means inverse Laplace transform of capital F of s is a small f of t, then L inverse of that of function f of s minus a is e raised to at into function small f of t. Let's take example. Laplace of cos of 2t is s upon s square plus 4 by the first table. Now apply this property with a as a minus 1. Apply this property with a as a minus 1, so that we have Laplace transform e raised to minus 1 into t, and ft we have taken as a cos 2t is equal to capital F of s minus of minus 1 means capital F of s plus 1, and which is obtained by shifting s by s plus 1, that is by changing s by s plus 1. And you can see that this is a function of s plus 1 because a is 1, a is minus 1 in the property, and you can no doubt you can simplify this, you can get it right. Now next example is here, inverse Laplace transform of we have to find inverse Laplace transform this time, 3s minus 4 upon s square minus 4s plus 20. So we require completing square adjustment. From s square we write s, from minus 4 we write minus 2, and then we take whole square and we find s square minus 4s plus 4. But we don't want plus 4 here, so we write minus 4, and minus 4 with the 20 became plus 16. And here in numerator you can take 2 common, or you make the adjustment because denominator is a function of s minus 2. So can you make the numerator also as a function of s minus 2? Yes. By making little adjustment, we can make the numerator also function of s minus 2, because denominator and numerator both are function of s minus 2. We are in position to apply the first shifting theorem for the inverse Laplace transform. So we have 2 terms here. So apply here, and you can see that a is 2 here in the first term, also in second term. So is 6 e raised to 2t, and by shifting this became s upon s square plus 4 square, and that is nothing but the Laplace that is actually inverse Laplace is cos of 4t. In second term again e raised to 2t, and you will find here you can see that here you find 4 upon s square plus 4 square, and which is nothing but the the inverse Laplace transform is sine 4t. Between these two terms e raised to 2t is common, and like this we obtain inverse Laplace transform by using first shifting theorem. So in last two problem we have used first shifting theorem for the Laplace transform, and in last example we have used the first shifting theorem for inverse Laplace transform. This is really very important property. Let's see a second shifting property, or it's also called as t-shifting. If Laplace transform of small f of t is say f bar of s, and g of t is another function whose value is f of t minus a if t is greater than a, and 0 if t is less than a, then according to the second shifting property, Laplace of gt is e raised to minus as into f bar of s. Let's see example, then we'll understand. We know Laplace of t cube is a 3 factorial upon s raised to 4, that is 6 upon s raised to 4. And suppose gt is a function which has two values, t minus 2 whole cube if t is greater than 2 and 0 if t is less than a. So this function has this type. A is a 2 and f of t minus 2 is t minus 2 whole cube, from which f of t became t cube, and Laplace of t cube is 6 upon s raised to 4. So apply this property. Laplace of gt is e raised to minus as. I said you a is 2, so e raised to minus 2s into f of t. F of t is here 6 upon s raised to 4. These are the references we have used for making this video. Thank you very much for watching this video. So today you have learned that how to use first shifting theorem, second shifting theorem and division by t theorem. Thank you very much.